Oh, so the airflow itself, um, I thought the way an engine exhaust manifold is like this, it like it's like a Y all the time, like that, and then it just like becomes a single pipe after that. The way it does that, that's how I'm going to distribute air. Um, so like, let's say this were the front of the bicep, right? And here's the forearm. Well, I'm going to have this tube coming this way, blowing air through it in this direction. It's going to be the cool air intake for the bicep area. And then these will all be the openings. And the air is going to come through and out these openings. And these openings can be lined up to go between the servo channels. So the air can go between the various servo channels. Alright, so this servo is closest to us, this one's a little further, this one's a little further. These represent different vertical channels. So this is going away from us. And these three tubes then could send air, I don't know, just spread it out, and it's gonna blow the air toward the proximal end of the muscle, which means closest to the shoulder. So, and then we'll have our vent tubes doing the same thing on the other side, and they are going to all merge into a single tube as well. And these will be drawing the air this way. So it's going to be just like an engine exhaust manifold here, except the engine shoots the hot combustion gases out from left to right and into one tube, which then goes out the back of a car. But in my case, I'm doing the reverse of that. This tube is going to be sending in the cool air and distributing it in between the various columns, the vertical columns of DC motors. And that will cool all the DC motors. And then because I'm having the air intake from the bottom, if the robot were standing up, it'd be like this. With this being the bicep bulge and this being the forearm, the cool air is coming from the bottom up, and then the exhaust is coming from the bottom up as well. And since heat rises, the heat was already going to be headed that way, so it's kind of going with the natural flow of hot air. So I'm going to have always cool air coming in from the bottom and coming out the top. And as we've already discussed before, the cool air is going to be intake through the nose, not the mouth, not the ears. The ears I want to maintain for um, microphones so that the robot can hear through the ears. And the mouth I want to reserve for the robot to be able to talk, or if he's not talking, he'll keep his mouth shut. And so I don't want him to rely on the mouth for breathing. Much like the human body breathes through the mouth when we're really out of breath, perhaps I could use the mouth in that fashion when the robot needs a ton of cold air if he's doing something strenuous. But for the most part, the breathing needs to take place from the nose. And there are no other cavities on the human body where he could breathe out and in, except maybe the butthole. If I gave the robot a butthole, maybe he could breathe out through his butthole. However, first of all, that's like farting. That's weird. I don't know if I want the robot releasing his hot gases through his butthole. Yeah, I mean, I could do it that way as an additional vent location, but I just feel like the robot should breathe out of his nostrils and in through his nostrils. Now, one concern I had is if he breathes in through the nostrils and out through the nostrils, wouldn't he be breathing back in the same hot air he just breathed out? I would say no. If that logic were correct, when a human breathes out through their nose, it form a little pocket of, like, let's say a little gas cloud that we just breathed out of carbon dioxide air with very little oxygen in it. And then if he breathes back in, he's going to be getting mostly oxygen depleted air. And I don't believe that's how it works. I believe that the way the human nose works, when we breathe out, the air really goes far and just spreads out throughout the room. When we breathe back in, it just pulls air, usually probably from the side of the face more, back in. And so the air we just breathed out is not going to be the same air we're breathing back in. So based on that principle, which I believe is the case, I think it's fine for the robot to breathe out his hot air from the same tube he breathes in his cool air. So the lungs will open up, drawing in cool air. They'll pinch off that, and then they'll blow out the hot air into all the different cavities of the body. And those cavities will then lead into various tubes that feed out this way and distribute it like that, and then the vent tubes will come out like that, all merging, just like an exhaust manifold. And the tubing will probably be vinyl tubing, or it could even be electrical wiring, like hollowed out, like this, where the copper is taken out, and that could be my tubing. Um, that would give me a lot of flexibility since I could use any gauge electrical wiring, slice it longitudinally, open it up, peel out the copper, and then reseal it back shut. But it wouldn't be really airtight. However, I don't think it needs to be airtight. It's just going to be a air guide tube. So if it leaked out a little bit of air, I don't think that'd matter. It's just like guiding the air. It's not needing to send pressurized air for actuation like a pneumatic hose or a pneumatic cylinder. Um, Even if you had a hole in your exhaust system for your car, it would just make noise, but it doesn't prevent your exhaust from working. It just causes little exhaust leaks. So I mean, I don't know. Maybe I'd glue the tubes back shut after removing the wiring, or maybe I'll just buy dedicated vinyl tubing. But I feel like I just have less flexibility in the gauges of tubing I could get if I did it like that. Like if I went to the hardware store to buy tubing, I feel like they just don't have a lot of sizes, and it's heavy. It's like thick walled, whereas the tubing that you can get from electrical insulation is very thin walled, and it just seems like it would be really nice to use that as the tubing for my air systems. Um, Another note on that, so let me get a fresh piece of paper. Um, so it's important to me that if the general flow of air in the robot's body is going like this, upward, that if I had a bunch of motors in the forearms, I don't want all the vent tubes to be up here, right? And all the cool air intake to be down here. And then that would mean that the motors at the top up here would be getting all the heat from all the motors all throughout here. I don't want these motors to get overheated because all these other motors are blowing upward. So I'm gonna compartmentalize the motors by muscle group. So like all the motors in the bicep region, I'm gonna put like a clear saran wrap wall, or maybe a vinyl or latex wall at the top and bottom of the muscle group, creating a separate compartment so that the heat generated by the motors of the forearm will stay in the forearm region, and they'll have their own vent system like this that runs up and out through the nose, and they'll have their own cool air intake, and then this will have its own cool air intake as well, and its own vent as well. And this vent can tie in with this vent. So the vent from each compartment can tie into a larger vent tube that combines all the compartments. Same thing with cool air intakes. They could all be interconnected, or they could be separate. I don't know if like I had a cool air intake that's coming like this, right? That's tubing. And then I took another tube and forked it again and did this for the forearm. And the cool air is coming this way. I don't know if this would get more air coming through than this would, because most of the air would take the path closest and it wouldn't want to make it down to the second fork. I'm not sure how that would work. Unless if maybe this tube were a little smaller in diameter than this one, and then equal amount of air would come through both. That's what Anna thought. Anna thought that if you're going to fork like this, when it comes to air tubing, you should probably, if this is much further away, the only way you're going to get equal air coming out of here and here is if the diameter of the fork is less than the main trunk. Because this is going further away, the air would want to take the path of least resistance, so it'd all go out this way. But Anna told me, no, as long as this one's smaller in diameter than this one, you should be fine. I don't know for sure, though. It'd be the study of fluid dynamics, really. Even for air, as air particles would be considered like fluid. It's interesting. And I would prefer to run tubing in a way that minimizes the amount of tubing, because space is going to be at a premium. Because I have to fit all of the electrical wiring, all of the motors, all of the electronics for the motors, all the control wiring, all the ventilation wiring, all the muscle wiring, all of that within the confines of the human body, so that when it's all said and done, it looks like a human arm. So I have to cram a lot of stuff into a very little area in order to maximize the amount of strength and capability of the arm and of all the parts. I'm just taking the arm as an example right now. For example, if I only fit 20 motors in the arm, it's going to be a very weak arm. It's not very capable. So the more motors, the more stuff I can fit, the better. So using less tubing would be better. So was Anna right, do you think, in saying that if your air intake is here and you want to fork the air in two directions, and this second one's going to be way longer, and this one's going to be exiting right here, this one's going to be exiting, who knows, maybe making turns and everything. maybe coming way down here. In order to have the same amount of air come out here as comes out here, wouldn't you want this tube to be smaller in diameter than this one in order to make sure that they both get the same amount of air coming out? How would that work, I wonder? So imagine you've got your artificial lung and it's squeezing air through a tube, right? The lung's going to squeeze shut, and I want to make the air split here and here. And hey, I want to make the air split again, maybe 3 ways this time, maybe 4 ways. Right? How am I going to ensure equal air is going out every opening? I need air to blow out equally, or how do I even control how much air is going to come out each opening? I just want to let it freely flow out of the lungs, blowing through all these tubes. So how would it distribute evenly? Or how would I be able to control if I wanted less air to come out of this one? But I just have it probably more restricted, right? Tinier opening. There won't be any valves. It's just all going to be tubing. The tubing is just guiding air. Air is being squeezed out of the artificial lungs, split into all over the body. Now, I considered I could do this. I could compartmentalize the artificial lungs, right? And then each compartment has an air tube coming out. And depending on the size of the compartment, that will directly control how much air is going through each tube. So that's a way I could distribute the air evenly, guaranteed, without worrying about air forking and ensuring air enters each fork at the proper amount. This would just be a guarantee. I could control how much air goes into each tube, and there's no forks. Each one of these tubes just goes to exactly where it needs to go. But that's going to lead to a lot more tubing than just having one tube that's a little bigger that forks out. This means just a lot of wasted tubing. It's a lot of wasted material. So I'd like to avoid using a system like this if I can just fork the air anytime I want. Sum of diameter of outputs of one branch has to be approximately equal to the other branches. Is that really the rule? Because that answers everything. So if that's the case, if I want this branch to equal this branch, then these tubes just have to be the same diameter. So it's all based on diameters of outputs. It doesn't matter the distance or anything else. We are ignoring distance. No, distance will be a factor. Imagine you have a fork in the chest, and it forks out to both legs, but then another fork in the chest just leads to the chest itself. That could be what? Let's say one of the forks just leads to here, and it's just cooling my right pectoral muscles. One of the forks leads all the way to my feet. Well, that's going to be a tremendous difference in distance. So distance is going to be a factor in this positively, and it can't be ignored. Where air exits is what builds pressure. You're not having more than 5 to 10 meters. Yeah, it'd be the difference between the lungs are going to be in the chest. So the furthest air output might be air output in the ankles of a 6'4" man. So that's what, like 4 feet? The closest output could be as close as 4 inches. So 4 feet and 4 inches could be the difference in output lengths from the source of the air, which is going to be the artificial lungs. The artificial lungs are going to serve as like a bilge pump. They're just going to suck in air, and then they're going to blow it out into the body. So in this example, the diameters of these four outputs have to be the same as the diameter of this output in order for these four. So let's say percentage based, this was let's see, 1, 2, 3, 4, 1. Alright, so this would be 10, 20, 30, 40. Let's just say 15, 30, 15, 30, that's 60 and 30. If this was 30% and these were each 15%, then 15, 30. So each of these would get half of that. But these tubes would have to be half that size. Oh, wait a minute. This would be 60%. So it would be, the first fork would be 60-30 in terms of the diameters. And then this could fork into all 15s, 15-30, 15-30. Is that accurate? So this one would have double the air of these outputs, because this is 30% diameter, these are all 15s. But in order for these 15s to get a full 15%, this one has to be 60%. The size, this is 30, this is 60. Because if I just split this as 30-30, these would not get 15. They would get some fraction of the 30. So these might get like 5%, and this would get 30%. So yeah, you can control airflow just by controlling the diameter of the various output tube forks. If you want to send more air, increase the diameter. If you want to send less air, decrease the diameter of the tubing. I'll be able to test all of my air tubing just by creating a mock-up artificial lung and just squeezing it by hand. And then I can feel the outputs of all the various tubes throughout the arms. And I'll be able to see how much air is getting through each tube. So I think that I have the confidence now with your statement. Your statement that I love the most was simple. The sum of the diameter of outputs of one branch has to be approximately equal to the other branches. So you add up the diameter of all the outputs, and then you add up the diameter of all the other outputs, and you can get mathematic estimations of how much air is going to be coming out. I like that a lot. Narrow equals faster airflow. See, that's really not relevant to me. I'm not concerned with speed of airflow as much as I am with total air volume being brought to the various portions of the robot's body. I don't think the speed of air matters in cooling systems. I think it's more how much volume of air is making it through. So as long as I have the right volume. For example, if you're trying to cool a room and you just take a huge fan, turn on very low, like a fan 10 feet in diameter, turn it on really low, that's going to send a lot of air into that room. Now I could take a tiny 8-inch or 1-inch fan and blow it 1,000,000 miles per hour, but that's still going to take forever to cool the whole room. So a larger volume of air is actually preferable, and speed of the air really is irrelevant in this situation, I think. You add length to the formula as well. So, in other words, if it's longer, as in this example, you got a lot more length than here, then this tube would even need to be bigger because the shorter length would tempt the air to come out the shorter, stubby end, and the air wouldn't bother to get through all this longer stuff. So this would need to be even bigger then to tempt the air to come that way. That's what I'm getting. So the longer the air has to travel, the more diameter you need for the tubes for that air.